So can you see the presentation? Okay. So this is our task to study about the energy and energy transfer. Okay. So if we went whatever the systems, okay. So as you are studying automobile technology, so there are various energy and energy transfer interactions are there. Okay. So let's say for the example, you are producing energy from where? So whole energy from the engine, no? Yeah. So using fuel, you are combusted and using that energy to produce the whatever the energy needed for the energy source, no? So basically the energy source for the your automobile is your engine. So otherwise, so if it is a electrical vehicle, then what is the energy source? Yeah, your battery. Okay, from your battery you are getting the uh, potential difference and you are running your vehicle or whatever. Okay, so if you get a push bike, what is your energy source? You are the energy source, you are pushing the bike, no? Okay, so that is how. So then to having an energy source, then you are having transmission systems, so like belt drive, chain drive, gears. So such energy transfer systems you are having transmission. So I think you have studied about these transmission systems. So in the so such things in very related to your course. So energy and energy transfers are very important. Okay, to study about this. It could be a thermal energy or work or whatever. Okay, so if you can produce a work, no, so that means the rotation of the crank. Okay, you are using the rotation of the crank all over the. So when you are running the vehicle, you are using the rotation of the crank, no. So that is a type of work. So as I already told you, all energy can be divided into work and heat. Okay. So then if you get a air conditioning system, so that is a energy transfer is there. Okay. You are reducing the temperature of the interior of your vehicle, no? So then you are having such energy transfer. Okay. So you are getting energy from your cabin and rejecting outside, such works you are doing. Okay, we will study about this energy and energy transfer systems, or so about those systems here. Okay, so as a thermodynamic analysis, right? First of all, have you hear about this one, conservation of energy principle? So in your school days, it could be a 8th standard or 7th standard, you have studied this one, conservation of energy principle. How many of you remember this? Can anyone tell me? What's that? Yeah. Hmm. Yeah. So that is the conservation of energy principle. Energy cannot be created or destroyed. You can't create energy or destroy the energy, but you can change the form. Okay. So from electrical energy to light energy or heat energy, or it could be a work. So if you are having a small motor using electrical energy, so you are transfer the electrical energy to work of the work output. Okay, that's a rotation of the shaft. Okay, so such things. Okay, you can change the form of the energy. So let's we consider about this. Okay, can you see the whiteboard? Okay. So you are having a room, right? So as we also discussed about this one earlier, right? We are having this room. Okay, this is well insulated. Okay, no heat interaction from outside to inside. Okay, you are having your refrigerator. Okay, one refrigerator that is open. This refrigerator is open. So what do you think about the temperature of the interior? So interior of this room, whole room. So there is a plug and refrigerator is plugged and on. Okay, on condition. So what is your idea about this room temperature? It will increase or decrease or will not change, or what do you think? So how it will increase or decrease? Increase or decrease? Okay, we can analyze this problem as this. So as our earlier statement, energy can't be created or destroyed, but you can change the form. Okay. Also, total energy in a system is conserved. That is the conservation of energy. Okay. So if the energy is coming inside only, so the total energy will increasing. Okay. If energy going outside, then total energy will be decreasing in a system. Okay. So if a system's energy is increasing, temperature will increase. That is okay, no? If your room's energy is increasing, that means temperature is increasing. So if the temperature is rising, you can say that energy is increasing. So in this system, so what happens? This refrigerator, normally refrigerators work is from the inside of the refrigerator take energy and release it to take the energy from interior of the refrigerator and release it to outside environment. Okay, so this is this one earlier in the air conditioning part also I have told you. Okay, but now the refrigerator is open. Okay, open mean so interior is same as exterior. Okay, so whatever it's getting, that will be rejected. Okay, so total energy is conserved. Okay, So from the refrigerator, you can't have any temperature decreases because the environment and interior is same no now as that this one is open. Okay. So but what happened here? Whatever this refrigerator is consuming electric. Okay, consuming electricity. That electricity is coming from somewhere outside. Am I correct? So electrical energy is coming inside. Okay, but as this one insulated properly, no energy can't go outside. So whatever the electrical energy coming inside should be stay inside the room. Okay, so this total energy or the temperature of this room should be going increase. Okay, right. So these are the some of the prior knowledge you are having about the conservation of energy principle. Okay, so in later on we will study about the first law of thermodynamics, such things. Okay, so first law of thermodynamics is nothing the same as this. Okay, so kind of energy balance or conservation of energy. Okay, we will study that one later. So before that, whatever the stuff related to energy and energy transfer, we will go through, and then later on we can understand first law of thermodynamics properly, right? Forms of energy. So what is the total energy of system? What is you are thinking? Anyone's idea? Yes. Mm-hmm. Okay. So anyone? Is my mic clear now? Okay. Switch on the fan buttons. Okay. So total energy of system, as she said, sum of numerous forms of energy, such as, so we are having so much of energy forms. Okay, if you take a system, okay, it could be whatever the system. So it could be your mobile phone or your laptop or whatever the system. It could be a automobile, it could be your room. Okay, or whatever the system. So those system have numerous number of energies. Okay, so such as thermal energy. Thermal energy means the because of the temperature of that is having energy. Okay, thermal energy. So mechanical energy, so if it is working some movements, okay, then mechanical energy. And because due to the pressure, okay, due to the pressure, there is a mechanical energy. Okay, and then kinetic energy, if it is moving something, okay, moving part, then kinetic energy. Then potential energy. Potential energy also, because of the elevational differences, there's a you are having potential energy. Okay, electrical energy, magnetic, chemical, and nuclear, such So combination of or the sum of these all the energies that called as total energy of your system. Okay, but in the thermodynamics we are not going to worry about the total energy of a system because it can't be measurable. Okay, so from a single atom the energies are defined. Okay, if you take a atom, so within the atom, so you as you know about the nuclear bombs and nuclear energy, so you might be here. Okay, so a single atom has much amount of energy that could destroy the stars. Okay, so from those atoms so much of energies are accumulated and everywhere energies are spread. Okay, so then from there you can calculate a total energy that is very difficult to calculate. Okay, and also we are not going to worry about the total energy of a system, right? But what we are considering is the energy change. Okay, that means, so from a reference point how much energy is changed. Okay, so if you having a water cup of water that is in 25 degrees Celsius, we are not going to worry about the what is the total energy of that amount of water. Okay, so we are going to worry, so if I increase the temperature by 1 degree, what could be the energy change? Okay, so that energy changes, so when 25 degrees Celsius, that is going to have an energy. 26 degrees Celsius, that water is going to have some energy. But we are going to worry about the energy change from 25 to 26 degrees Celsius, increasing the temperature. What is the energy change? Okay, so between two reference points, what is going to be the energy change? Such thing. Okay, so then in a reference point, okay, in a reference frame, we are going to uh, put like the total energy is say 0. Okay, that means, so then 25 degrees Celsius, 0, 25, 26 degrees Celsius. Then what is the energy difference? Okay, so then we don't want to worry about what is the total energy of this point. Okay, we are going to for from here to increase 1 degree Celsius. So as we know, 4.2 kilojoule per kilogram degree Celsius, that is the uh, specific heat. So that amount of energy we have to give. So that is only we worry. Okay, so there we are having another stuff. Okay, that is this total energy we can divide into two types. Okay, so that means the forms of energy you can classify into two types. Okay, so as one is microscopic energy and other one is microscopic energy. Okay, macro and micro, from the name you can understand what is micro and macro. Macro mean energy are those a system possesses as a whole with respect to some outside reference. Okay, so from some outside reference, uh, that's you can calculate, or that means the potential energy or kinetic energy. Okay, so if a vehicle is or vehicle or whatever the object is not moving, okay, we can tell that as kinetic energy is 0. Okay, and if a reference place, we can say that the potential energy is zero, and if it is go above, that will have an energy, go below, so that will have an energy. Okay, so energy with the directions. So but microscopic energy is related to the molecular structure. Okay, so degree of molecular activity, so that won't depend on the outside reference. That means if you go to the molecular level, okay, intermolecular bonds are there. Okay, intermolecular bonds, that means to molecule to molecule, so there are bonds and molecules are moving, vibrating. Okay, so if you take an atom, then atom's nucleus is there and electron is always spinning. Okay, so such things, so in the molecular range or the atomic sizes, so every small subatomic particles are vibrating, rotating. Okay, electron cloud and every movements are there, so those kind of energies. Okay, so they are having a magnetic field. Okay, such thing, right? So then, so if you have an iron bar, so that having many amount of iron particles are there. Okay, that means the atoms. Okay, so the atoms are always vibrating. Okay, always they are vibrating or oscillating. Okay, if you give a heat, the oscillation will go high. Okay, so they don't have a reference, so you can't say that, so there is a reference, this is zero, because they are always doing something and they are having so much of energies. Okay, so that is the microscopic energy. So macroscopic is normally what you are dealing with. Okay, so some of the all microscopic energies we can tell as internal energy. Okay, so with the temperature and normally with the temperature we can say this internal energy of the system changes. Okay, that means the molecular activities will be activated. Okay, so if you take an iron bar, if you are give a heat, okay, molecular vibration will be increased, then their internal energy is increasing. That means likewise, I am walking. Okay, I am always walking. If I am always walking, I am having a kinetic energy of me. Okay, so that means I don't stop working. Okay, then always I am having a energy. In the reference you can't tell me, so I am having a zero energy, right? So if the flow temperature is increasing, so what I will do, walking person will try to run, no? So I will run, then then what happen, my kinetic energy will be increasing. Okay, so with the temperature, your internal energy is changing. Okay, that means the molecular activities, when the molecular activity is changing, okay, with the temperature or whatever, then your microscopic energy states will be changes, right? So macro, no, normally we are worrying about this macroscopic energy, and sometimes this internal energy of the system also we are worrying. Okay, so we will see those things, how we analyze those stuff and how we can classify next slides. Okay, what is a kinetic energy? So these stuffs you have studied in, from your childhood, no? What is kinetic energy? Just someone or the equation. Can you hear me? Yeah. What is kinetic energy? I think only Rukshan and Kausalya is answering. What others doing? Okay. Motion of the energy. Oh, what is it? Udhishthran, what are you thinking? Yes. Yeah. What you are thinking about kinetic energy? Mass and speed. Okay. What is that? Yeah, because of the object's motion, right? So that's the energy of the system possesses as a result of its motion. Okay, relative to some reference plane. That means, so if a car is moving, let's say 100 kilometers per hour. Okay, is it actually moving 100 kilometers per hour? Did you think about this one? So if a car is moving 100 kilometer per hour, okay. So let's say Jeffna to Kilnachi, okay. So you can tell that is moving on 100 kilometers per hour if and only the land is not moving, isn't it? If the land is fixed only, that is moving on 100 kilometers per hour, but the earth is rotating. Am I correct? Earth is rotating, okay. So earth has a movement, but by making the reference frame as earth and assuming that earth is not moving, you are saying 100 kilometers per hour, right? So same as, so one car is moving 100 kilometers per hour and the same direction another car is moving 80 kilometers per hour. For the 80 for the one who travel in 80 kilometers per hour, he will feel like the 100 kilometer per hour car is moving like 20 kilometer per hour. Okay, that's a relative velocity theorem. Have you heard about this one? Relative velocity. Okay, so when you are having a such relative to some reference frame, relative to reference frame, so result of the motion, the kinetic energy we are defining. That means, so in your table, okay, in your table, let's say you are having a pen, okay. In your table you are having a pen. What is the kinetic energy of that pen? That pen is not moving. Zero. Okay, zero reference to what? To the earth. Okay, but earth is rotating now. Earth is rotating. Because of Earth is rotating, because of the gravitational, as the same angular velocity, that pen also rotating. So if you go to the space and watch the pen, what you can say, the pen is also rotating, so that's having a amount of kinetic energy. Am I correct? Yeah. So whatever the reference you are having, okay, that is the macroscopic energy. So you should have a reference plane, okay, reference frame, right? To the reference result of the its motion, okay, kinetic energy is defined. Are you clear? Or I am complexing? Yeah. So we can say the kinetic energy, the equation as mv squared by 2 or half mv squared, right? Kinetic energy we can define as half mv square, okay. Kinetic energy, okay, in a unit mass basis, okay. So have you hear about this specific properties? Have you ever heard about the specific properties? Anyone? Why? So what you have studied in the last lectures? Properties we can divide into two parts, okay. So two, we can classify into two different properties. What is intensive, extensive? Intensive properties are not depend on the mass or size. Extensive properties are depend on the mass, okay. So the extensive properties we can go for the specific properties. That mean if for the intensive properties we can say pressure, temperature, such thing. Extensive properties, total mass or total volume or total energy. Okay. Have we go through these stuffs? Yes or no? Yeah. So if we divide any extensive properties with this mass, okay, with the mass, so that will give the specific properties, okay. So that means if the total volume is V, if you divide this that by the total mass of the system, that will give you the specific volume, right? Specific volume. So if the energy is there, total energy E divided by its mass, that will give you the specific energy, okay. Specific properties we are notating in small letters. Extensive properties we are giving in the capital letters, right? So that is about the specific properties, okay. So specific properties simply unit mass basis, okay. So the kinetic energy also depend on the mass, isn't it? So kinetic energy is extensive property or intensive property? What is intensive property? Intensive is not depend on the mass. Okay. Extensive. Extensive you can uh, memorize as extension. Okay. Extension mean that is always worrying about the size. Am I correct? Extension. Okay. Extending. Okay. So that is depend on the mass. Now the kinetic energies depend on the mass or not? That is depend on the mass. So we can say this kinetic energy is extensive property. So we can write the kinetic energy in unit mass base. That means as a specific property. Okay, that means specific kinetic energy, right? That is equal to half v square. Okay, specific kinetic energy of unit mass basis. Specific kinetic energy is half v square, right? So that means K E by M, mass of the system, right? So have you studied about this one, kinetic energy of a rotating body? What do you think about this one? Have you studied about rotating bodies in the science for technology? Science for technology? No one is answering. Yeah, half of omega square. Right. So I is moment of inertia. Omega is rotating velocity. Yeah, angular velocity. Right. So just substituting for m and v. Right. What is potential energy? Yes. Okay. Or actually the elevation. Okay. Elevation. Position mean you, so you can get position like this also, no? So if you have a field like this, set is 0. Okay. So this is also a position. This is also a position. This is also a position. Okay. But now this and this sign same reference level. Okay, these two are in same reference level, but this is also another position, but that does have a height difference, no, elevation difference. So there should be a elevation difference for the potential energy. So when elevation is going high, your potential energy is going high. That means that potential to come again to the ground. Okay, so ground mean the set is equal to 0 position. Okay, zero elevation. So, and there should be a gravitational field also. If there is no gravity, potential energy you can't define. Okay, you can't define a potential energy. So, potential energy is mgz, or in earlier times you might have studied as mgh. Okay, h is the height. So, height is the elevation difference. So is that here we are defining as the elevation difference from the reference plane. Okay. So there also should be a reference plane. So if you are sitting sitting on a bed, okay. If you are sitting on a bed, your bed surface is the, you might assume like your bed surface is zero potential line. Okay, zero potential surface. Or you can define as your whatever your floor is the zero potential level, right? So that is according to what you are assuming. Okay, so there also should be a reference point. Okay, signal lost, what happened? Okay, equation for total energy of a system. Okay, so let's we try to write a equation for total energy of a system. Okay, with the notations only. Normally for this normal general systems, okay, general systems in normal, whatever you are seeing the systems, or you can take, whatever, okay. We can neglect the magnetic field and electrical field, okay, and nuclear energy and those stuffs we can neglect, okay, because they are not going to, okay. These surface tension effects, okay, so they are, we are neglecting, because neglecting mean absence of those effects, okay. So we neglect the presence, okay. So assuming that, so in our system, okay, for this basic concept only, okay, for our system, so they are not here, okay, so they are not presenting here, so they are absent, okay. Then we will have, for a system we will have, what are the stuffs we will have? Kinetic energy, potential energy, and because of the all the microscopic energies we are having, what, sum of all microscopic energies, we are having internal energy of the system, okay. So by using this, we will try to construct a equation, okay, equation for the total energy of the system. So we can write like this, okay. total energy of the system is equal to internal energy of the system plus kinetic energy of the system plus potential energy of the system. Okay, so that means U plus mv square by 2 plus mg z. So the SI unit is kilojoule. So what do you think about the stationary systems? Stationary system mean, okay, so they are staying, they are not moving. Okay, if they are not moving, we can say that is stationary. Okay, if they are not moving, okay, the not moving mean no movements are there. So if there is no movements, what will happen? Kinetic energy will go zero, right? So normally for the closed system analysis, we are assuming that so if it is not given um, uh, for the closed system analysis, if nobody told about anything about the movement of the system, okay, so velocity of the system or movement of the system, you can assume that as that system is stationary. Okay, assume as stationary. So that means that doesn't have any movement, then you can neglect the kinetic energy part. Okay, so closed system whose velocity and elevation of the center of gravity remain constant during a process. Okay, center of gravity is, so you might have studied those stuffs. Okay, so if you can balance a scale, okay, like this, then the center of gravity is that point. Okay, so for the all objects you can uh, calculate the center of gravity. Where is the center of gravity? So where is your center of gravity? Do you know where is your center of gravity for a human body? So that is in your belly, no? So in your belly button, so your center of gravity is there. Okay, so for a stationary system, so if you assume any system to be stationary, okay, then there is no movement, right? There is no movement, and center of gravity remain constant, that doesn't change. Okay, these are some basic stuffs. Okay, basic stuff mean these are some analytical stuff, they are you are going to use in future calculations and analysis. Okay, so that's why I included this one. So what is a volume flow rate of a system? What is the volume flow rate of a system? So normally in the open systems we are having this volume flow rate analysis. Okay, open system. Closed system means no mass interaction. Okay, but there is energy interaction. But in an open system, that is open. So let's say a pipe like this. Okay, this is an open system. That means mass can come in, energy can go in, or mass can go out, energy can go out. Okay, so if mass is coming, that means let's say this is a pipe channel. Okay, pipe channel, and water is coming inside and going outside. Okay, so that is having a volume flow rate v dot. Okay, volume flow rate. If this word comes, okay, rate, flow rate, if the rate is comes, that depend on the time. Okay, time means for unit time what is the change? Change in unit time. Okay, so if you take uh, a velocity, okay, if it's a velocity, that is rate of changing distance. Okay, distance by time, rate of change of distance. Acceleration means rate of change of velocity, right? In a for each unit time, what is the amount changing? Okay, so volume flow rate mean, so in the name you can understand, so there is a change in flow. Okay, in what is the flow change in unit time, right? So the flow rate is what is the in which rate the water or whatever the liquid is coming, liquid or uh, gas or whatever, right? So that means this cross sectional area, okay, let's say in a velocity average, okay, in an average velocity v average and cross sectional area AC, these are the parameters. In this velocity the water is coming. Okay, what is the volume flow rate? V dot is equal to AC into V average. Okay, volume flow rate is equal to AC into V average. So also you can define the mass flow rate. Okay, mass flow rate. Earlier that one volume flow rate. This one mass flow rate. Mass flow rate mean, so in a unit time what is the change in mass flow? Okay, earlier volume flow. So mass flow mean, what is the equation for mass and volume? What is the relationship with mass and volume? We can tell density is equal to mass over volume. Okay, so mass you can tell as density into volume. Okay, so we can directly put here mass flow rate m dot is equal to, right, density into volume flow rate. Okay, here you can see notation dot. Okay, v dot, m dot, okay, e dot, or whatever, velocity dot, or you can write several dots. See, these dots are referred to rate. Okay, change in a unit time. Okay, so if the this velocity I can write as d dot, acceleration I can write as small v dot. Okay, velocity dot, like this I can write. Okay, so dot means the change in unit time, right? So mass flow rate m dot is equal to rho into v dot. So v dot I know, rho into AC into V average. Okay, I can write as mass into this mass flow rate is equal to rho into AC into V average. So mass flow rate of a system, energy flow rate of a system, right? Energy flow rate. Energy flow rate is E dot. Okay, that is I can write as mass flow rate into specific energy flow rate, right? So if I can calculate what is the specific energy of energy flow rate of a system, then I can easily calculate what is the energy flow rate of a system. Okay. So AC is equal to pi d square by 4. So that is, you know, okay, this cross sectional area. AC cross sectional area. Okay. What is a static form of energy? Okay. Static is no movement. Okay, no movement mean, so as we can say as stationary. Okay, so that is the static. Okay, static form of energy is, what is the static form of energy? Hmm? What do you think about the static form of energy? Anyone? So there is no movement mean that energy is not transferable. Okay, the energy are not transferable, though those are called as static form of energy. Okay, so other one is the dynamic form of energy. Okay, dynamic form of energy mean the energy does transfer. Okay, in two forms of energy can be transferred. Okay, so only two forms of energy can be transferred to from one system to another system, or environment to system, or system to environment, or whatever. Okay, so what are the forms of energy? That forms of energy is heat transfer. Okay, other one is work. In these two forms only can be interactable. Okay, That means these two are the dynamic forms of energy. Okay, transferable forms. Then we can study about the mechanical energy. Mechanical energy is, so it's we can say that is about the pressure. Okay, so earlier in the equilibrium conditions also we have studied about the mechanical equilibrium. What is a mechanical equilibrium? If the pressure is doesn't change, we can say that is in mechanical equilibrium. Okay, so pressure in the equilibrium conditions, then we can say mechanical equilibrium. Okay, so pressure means, so where the pressure are involved? What do you think? Where you are think the pressures are involved? Then energy transfers. Okay, if there is a fluid flow, okay, if there is a fluid flow, that is pressure involves, no? So from your, so if you are having a well in your home, you are putting a pump, okay, water pump. You are putting a water pump and send the water to your tank. Okay, you suck your water from the well and and send it to pressurize and send it to your tank, isn't it? So when there's a fluid flow is involved, you are having this mechanical energy. Okay, that means, so why we are going there? Okay, we talk about related to your um, whatever your course. Okay, automobile technology. So if it is automobile technology, how many pumps are involved in the automobile? So many pumps are there, no? So what are the pumps you have studied? Yeah, oil pump. Yeah. Yes. What else? Hmm? What's that? Foil. Ah, fuel. Fuel. Ah, what else? In power steering pump is there. Okay. So several pumps are there. So all the pumps are related to what? Some fluid flow, no? So some fluid flow is needed. You are putting a pump. So what you are doing with the fluid and pump? You are pressurizing the fluid. Okay. So fuel is in your tank. You are give the pressure to the fuel to go to the combustion chamber. Okay, supply to the combustion chamber with a pressure. So when that is going to the from the nozzle, so for the at the nozzle you should have a certain pressure. Okay, so that pressure, all the pressure losses, calculating all the pressure, you are putting a fuel pump. What else in uh, engine cooling system? You are having water pump. Okay, so water should go through all the way of the engine. So, so to the movement of the water or the coolant, you should have a pump. That pump is giving the pressure to the fluid and that is going all through the system, right? That is the fluid energy. Okay, giving a energy to the fluid. Okay, by giving a pressure. So mechanical energy, the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. That is a mechanical energy. So, do you know any turbines? Do you know what is a turbine? Yeah. So, we are having two types of stuff that is called as turbine and pump. Okay. Pump is converting that mechanical work to pressure. Okay. Turbine is converting pressure to mechanical work. So that means, so you, in your homes, you do you have any fans, table fan or something? Okay. If you give electrical work to that table fan, that will rotate. Okay. If you supply air to that fan will rotate. Am I correct? Yeah. So now you are giving other way. Okay. You are giving air to that fan to rotate it. So when that is rotating, that air is the energy in the air is converted to mechanical work of the fan. Okay, that is simply a turbine. So such thing. So in dams, near to dams, you are putting turbines. Okay, to get the electricity, dynamo and turbine. Okay, generator and turbine. So the pressure energy or the pressure in the water is converted to mechanical work with the turbine. Okay. So if you are having an ideal turbine, that will convert all the pressure to mechanical work. Okay. All the pressure to mechanical work. Okay. So but the turbines are we are having, so near to 98 percentage efficiency are available, but ideal turbine is we can't actually build it. Okay, but we have just go near to 98 95 percentages. The pump is transfer mechanical energy to a fluid by rising its pressure. Okay, as I earlier just said. Okay, turbine extract the mechanical energy from fluid by dropping the pressure. Okay, so anyone went to any this power generation fields near to dams? Anyone visited? Yeah. So that fluid energy has so much power, no? So if you put that through the turbine, okay, after that, that fluid speed is reduced. Okay. If you are not putting a turbine there, there will be a big splash there. The fluid will come with very fast. Okay. And speed is very high and pressure is very high. Okay, then the damage that could make is very tremendous. Okay, but if you put a turbine there, turbine, after passing through the turbine, the fluid will get slow down. Okay, and then and the pressure is reduced. Okay, what happened? So the turbine extract, okay, turbine extract all the mechanical energy from the fluid. Okay, now the fluid is slow down. Why? The energy is extracted now from the turbine. By using the turbine, energy is extracted. So now that got slowed down and going out. Okay, otherwise the pressure will be very high. Okay, that is how they are producing electricity from the these very big dams. Okay, water reservoirs. So uh, you know about the pressure from the, if you are having this um, if it is a dam, okay, so this is water, this is the datum level, okay. Here pressure is atmospheric pressure, PATM, okay. So this height is h. What could be the pressure here? P is equal to PATM plus h rho g. Am I correct? Yeah. So here you are opening the tunnel and here putting your turbine. Okay. Here you are putting your turbine. So the pressure will be P plus H rho G here and here P ATM. Okay. This is the dam. Okay. This is your turbine. Okay. So the energy that having here is very high, okay, very high energy. So you know about the height of a dam, okay, you know height of a dam, that is so many meters, no. So that amount of pressure energy is here, okay, you are using that energy, okay, and to produce the electricity, okay. Okay, a pressure force acting on a fluid through a distance produce a work called a flow work. Okay, so if you get a pipe channel, okay, so due to the pressure force acting, so that fluid is moving now. So how the fluid is moving? There is a pressure is acting. Okay, so uh, if you want to move a object in your table, you have to give a force. Am I correct? Okay. Yeah. If you want to move any object in your table, you have to give a force. Okay. So what is pressure? Force acting on a unit area. Pressure is equal to F over A. So if through a channel your object or the water is moving, okay, if the water is moving, there should be a force. That force acting on this cross sectional area. So then we can calculate what is the pressure. So that is actually the pressure. Forcing act on unit area. Okay. In 1 meter square area, what is the Newton force acting? Okay. That is the pressure. So this Newton meter minus 2 or otherwise this amount of pascals. Okay. So that is how we are defining the pressure. Right. So as you know earlier, in your small childhood you have studied, if you are mm, applying a force here and move this object by x distance, then the work you have done to this box or the object is f into x. Okay, so such here you can apply. Okay, that is the work done. So you are moving here fluid that is flowing in mass flow rate m dot. Okay, so now as you are applying pressure, you are applying force. Okay, force into distance, so that is going to be the work done on this pressure into volume, right? So volume flow rate, actually. That is the there is a work done on this fluid. Okay, that is called as fluid work. Or the flow work. Okay, so the mechanical energy flowing fluid can be expressed as on a unit mass basis. Okay, unit mass basis mean that is specific property. Okay, specific energy. Okay, so you can in the specific energy specific property means the unit mass basis you can express like as this. Okay, the the mechanical energy of a flowing fluid E mech. Okay, that is P over rho plus V square over 2. Okay, this is the pressure energy. Okay, energy due to pressure G set. This is energy due to the movement. Okay, kinetic energy. This one is energy due to the elevation difference. Okay, potential energy. Right. So that is unit mass basis, and this one is rate of energy change. Okay, rate of total energy change. So then we have to multiply this specific energy with the m dot. Okay, mass flow rate. Then we can calculate the energy flow rate. Okay, energy flow rate, in which flow energy is transferring. Okay, take this example to understand about this one. Okay, so here, so this one first state and this one's fourth state. Okay, I put here this area 2 and this area 3. Okay, now we will analyze here what is the energy changed. Okay, what is the energy change? Oh, the energy change is equal to work produced from the turbine. Am I correct? From this point to this point, what is the energy change is equal to amount of work produced by the turbine. Okay, so in first position and fourth position, you know pressure atmospheric. Okay, pressure atmospheric PATM, right? So the velocity that is decreasing in this direction, and it will increase in this direction. Okay, that means whatever the amount of water coming there, that will go there. Okay, so if it is a very big dam, okay, this velocity we can, these two velocities we can neglect. Okay, v1 and v4 we can neglect. If it is a very big dam, then very big amount of water will come, and no changes in elevation, no, so we can neglect that one. So as here written, okay, work max produced, that means the turbine is assumed as ideal turbine. Ideal turbine. Okay, m dot as earlier one, m dot e mech, m dot e mech is equal to pressure by rho plus v square by 2 plus g z. Okay, so that is pressure here P atm. Fourth one P atm by rho plus v square and v square, because both are same, no, v1 and v4, by 2 plus here what's the difference, elevation difference, g h minus g. So if you put like this as 0 potential level, that is equal to 0 g into 0. Okay, work produced is equal to gh. Okay, that is in unit mass basis. If you multiply with the m dot and gh, capital W dot is equal to m dot gh. Okay, so here we have to multiply by m dot. Okay, this by m dot. So m dot gh is the work produced. Okay, so as we know, okay, as we know, for this point 2, okay, for this point 2, what is the pressure in point 2? What is the pressure in point 2? Let's say point 2's pressure is P. Okay, so from this reference point 1, what is the pressure of point 2? P is equal to rho g h. Okay, pressure is rho g h. We will go to this 2 and 3. Okay, we will go to this 2 and 3 analysis. This is your turbine. Here I put P. This is ideal turbine. Okay, here we will apply the E. E mech is equal to P by rho plus V square over 2 plus G Z. Okay, right. Now we will apply for this one 2 and 3. E mech is equal to, at 2 pressure is P2, right? At 3 pressure is, all pressure in energy is extracted now by the turbine, ideal turbine. So their pressure is, I can put as 0, right? By rho plus v square of by 2. The velocity can be neglected. Okay, so both velocities will be, so why, so whatever the amount of mass coming in will go at the same rate, no, because this is control volume. Volume is controlled. Okay, volume is controlled. So if you take a pipe, so whatever the water coming in is going out. So any water is staying there inside. The at this situation, the same amount of water will always, the volume of the chamber is same. So whatever the water is coming in will going out. Okay, Are you clear? So m dot 2 and m dot 3 are same. That mean m dot 2, m dot 3 are same. That mean row v dot 2 and row v dot 3 are same. That means v dot 2 is equal to v dot 3. Okay. Then I can write as AC velocity average 2 is equal to AC velocity average 3. AC are same, no? So velocity average 2 and is equal to velocity average 3. Okay. So velocities are same at 2 and 3. So velocity 2 and 3 are same. So I put V and V, V minus V over 2 plus. So this elevation difference I can neglect, no? Elevation difference I can neglect. So now I can write as Emec is equal to P2 over rho. Okay. So what is the work produced? Work produced is equal to m dot into E mech. That is equal to m dot P2 over rho. Okay. What we have got earlier for the work max produced mgh. Okay. mgh. From the earlier equation, that is mgh. mgh m dot. Okay, m dot gh. Now those work max are same, no? Same are produced by the turbine, whatever the turbine used. So mgh is equal to m dot p2 over rho. So p2 I can write as m dot cancel p2 rho gh. So our equations are correct. Okay. So you know earlier also you know this p is equal to rho gh. Okay. In counterpart we have, so by using this workmax equation we have again showed that the same is coming. So workmax calculation is same. So workmax we can calculate like, so that could be m dot gh or p2 over rho m dot. Okay. Right. Any doubts? Any doubts? Yes. Anyone having any doubts? Can you hear me? Yeah. Anyway, you are having doubts? Rukshana? Yeah, no doubts. Kausalya? Afla? No. Chamika? Yeah. Do you have any doubts? Okay, then I won't share these slides with you, okay? Because I told you to write your own notes now. It's okay, but I gave you all the instruction to create your own notes, okay? So one, so as you are not having any these laptops, only 15 people are having, so I can't give any assignments. So that's why I gave you some tutorials works, okay, worksheet and tutorial. So go through that one and prepare your own notes, okay. When we are meeting there, we will see your notes, each ones, okay. uh, yeah, you should write. So in your exercise books you can write. So if you take the worksheet, okay, if you take the worksheet, you can try. The thing is, everyone doesn't have that. Okay, so in this worksheet, so the problem Rukshana said is everyone doesn't have laptop facilities, isn't it? So if you don't have a laptop facility, then it's wrong to give assignments like do your in Word or Word file or whatever and upload. That is wrong. No? So whoever having Word and accessible to Word and other thing, you can create your own notes with there. Or you can create the notebook in Teams also. So in the Teams, there is an option for notebook. So there also you can create, but other people can do with the normal notes what you are taking. Okay. So if you take this worksheet, okay. So instructions are given, the task. So task, everything are given. So how you have to search in the internet. Okay. What are the things you have to search in the internet, and what are the things you can search for the in YouTube video also available. Oh. YouTube videos also available. Okay, so you can go through that also, and I will upload this video also. To today's video, I will upload. Okay, so those who can access to download this video, okay, no problem. So all the instructions are given actually here, so you can search and find out and be ready with that. So when we are meeting, you can show your notes. I will check. Okay. So this, yes, tutorial. These questions are there. No? So can you see this one? Yeah. So this is normally what you have done in your science for technology subject. No, it's slightly same as that. So everything you are going to study in the thermodynamics are physics and chemistry stuffs. Okay. So some of the stuff you have already studied in science for technology might be okay. So using those physical equations, you can solve this. Try to solve this. I will put a tutorial class for this one. Okay, how to solve these equations and questions. Okay, so then we can see there.